Yes. Hello. Can everyone hear me? Okay. Okay. So yes, I want to be presenting today a version of Hoffman and Stryker's groupoidal model of Martin-Löf type theory. Is additional, got an algebraic flavor, and also can be done in internal groupoids rather than just set-based groupoids. So when I say model of Martin-Löf type theory, I mean comprehension category, which luckily Nusha spoke about a little bit, so I'm not going to talk too much about this. But what I want to note about this definition is that this category F, which appears in this definition, is normally some kind of class of vibrations in some way. And yes, such data gives a weak model of Martin-Löf type theory. I guess it gives a strong model of CCTT, and maybe that's an important difference to note. It gives a kind of some of the types you want might be kind of pseudo in some way. So an example is given by the groupoid model of Martin-Löf type theory. So you consider the class of isofibrations, where isofibration between groupoids is a functor between groupoids, so that you can lift paths in the base. So if you've got a path in the base from B to some FA, you can lift it to a path in A that lives above it. Another way to say this is to specify that the map that does F on morphisms and also considers the targets map has a section. This is just the same thing. So, and this provides an example of comprehension category. It's the inclusion of the class of isofibrations, or I guess the category of isofibrations into the maps in groupoids forms a comprehension category. And hence gives a model of Martin-Löf type. So many more examples appear as examples, or many more examples are found by weak factorization systems. So a weak factorization system is a pair of classes of maps in the category, such that every arrow can be factorized as a left map followed by a right map, and these maps lift against each other. So left maps lift against right maps. So this is kind of studied, for example, in Pietrangelo North's PhD. So some examples of this. Isofibrations appear as the right class of a weak factorization system on groupoids, where the left class is injective on objects equivalents of groupoids. And these form the model of Martin-Löf type theory. Another example is given by Kahn fibrations on the right, and monomorphic multiple equivalences on the left. And this is a weak factorization system on simplicial sets. And this is well known to give a model of homotopy type theory after the Wodski. So kind of an intuition for what's happening here is that the kind of extra structure of the left class of maps gives you kind of some things to say about identity types. So the idea is that if you factorize the diagonal map into a trivial cofibration, a left map followed by a right map, then this right map will give you a type in your type. But one of the problems is that this kind of choice of path objects can't be made to be coherent immediately. And this has to do with there being the mere existence of a lift between left and right maps, rather than the structure of a kind of coherent choice of lifts. So a solution to this was suggested by Richard Garner in moving to a more algebraic setting, having actually choices of these lifts that behave functorially in pyramids. So this idea was taken seriously by Gambino and Larrett in a paper where they define the notion of a type theoretic weak factorization system. So this is an algebraic version of a model of type theory, where we consider a pair of comonad and a monad, so algebraic structures, such that they kind of have an underlying weak factorization system. The coalgebras are kind of the left maps, and the algebras for R are the right maps. We have to close these under retract, but never mind that for now. We also assume that we have some extra structure and they satisfy some extra conditions. But I guess their main result is that such a thing, type theoretic algebraic weak factorization system, forms a nice model of Martin-Löf type theory. And in this type theory, the F algebras model the dependent types of this type theory. Okay, so we're going to move from these isofibrations that we'll consider in Hoffman and Stryker's model to a more algebraic notion. So this is the definition of an isofibration. We define a cloven isofibration to be a pair, an isofibration, together with not just the existence of the splitting, but a chosen section of this map. And so this pair is a cloven isofibration, and it's kind of taking along some algebraic data with it. And here's the proposition: there exists a monad on the category of groupoids, or the arrow category of groupoids, such that the algebras of this monads are precisely the cloven isofibration. And this is quite nice. And you can use this to show that there's a type theoretic algebraic weak factorization system involving F. And so hence these cloven isofibrations form a model of Martin-Löf type theory. So interestingly, in this type theory, we can have one isofibrations with two different choices of splittings. And in the type theory, these will be actually different types. So this type theory is kind of sensitive to kind of lifting parts, so lifting identity types. So maybe this gives you a hint of why this kind of algebraic framework captures coherence of identity types in some way. Okay, but we can do this in a more general setting. So if we recall the definition of a groupoid, this is a pair of sets, C0 and C1, and some maps, source and target, which make it into a graph, an identity morphism, and a composition morphism, which make it into a category, and then a kind of inverting arrow morphism, which make it into a groupoid. So this is the definition of a groupoid, a small groupoid. If we replace the condition that these have to be sets, these C0 and C1, with the condition that they have to be elements of some other category E, this is the definition of an internal category. So all we need in this category is for there to be callbacks. Because of how we phrase this, so we've got C1 and C0 now, we can give the definition of an internal cloven isofibration in exactly the same way as we gave this definition of a cloven isofibration in groupoids. So again, we must have the existence of this splitting of this map. So okay, this works for any category E with callbacks. We're going to now form a model of Martin-Löf type theory, where the internal cloven isofibrations are your types, but we must assume a couple of extra conditions on E to make this work. So we're going to assume that E is a locally Cartesian closed extensive category in which the forgetful functor from internal categories to internal graphs has a left joint. It's maybe a bit abstract, but don't worry, I'll give some examples of such an E in a bit. But if we have this setting, then I guess the main theorem is that there is a monad on the category of arrows of internal groupoids, such that the algebras of this monad are exactly the cloven isofibrations, and these form a type theoretic algebraic weak factorization system, and so give a model of Martin-Löf type this way. Okay, so I'm going to talk about some examples, but first I'll talk about some non-examples. So we can't apply this for E equals cat, or for internal categories, or for abelian groups, because these categories are not locally Cartesian closed. And we really need local Cartesian closure in order to be able to find pi types. Okay, so some non-examples, assuming all of the pseudo middles. If we take E equals set, this satisfies the thing and gives a kind of algebraic version of Hoffman and Stryker's groupoid model, Martin-Löf type theory. We can also do this for any pre-sheaf category. So by noting that kind of pre-sheaf construction commutes with the groupoid theory, then we get kind of indexed version of type theory, in which our types are indexed by some other category. So you're kind of lifting the first example or types into a kind of indexed version of this. We can also do this for any groupoidic topos, so for any sheaves in some category, and get kind of a sheafy type theory, a geometric type theory. It's quite nice, where our types, I guess, glued together in some way. More foundationally, I guess we can do this for any elementary topos with a natural numbers object. But we don't actually need the I'm going to call it a script. We don't need the subobject classifier at all, so we can actually just do this for any arithmetic pi pretypes. So if you don't know what this is, you can just think of it as a elementary topos with a natural numbers object without the subobject classifier. And actually, these arise as syntactic categories for Martin-Löf type theory themselves. So if you start with a Martin-Löf type theory, form its syntactic category, this forms an arithmetic pi pretopos a certain way. And if we take groupoids in terms of this, we get a model of Martin-Löf type theory. So this kind of gives a relative consistency result. An instantiation of this is a model of Eric Palmgren's constructive elementary theory of the category of sets. So this gives a kind of constructive version of Hoffman and Stryker's groupoid model of Martin-Löf type theory. And another example, which uses kind of the full abstract version of this theorem, is category of assemblies on some partial combinatorial algebra. So these are things that such that the exact completion of them becomes the effective types, or a realizability. So to speak about some future work, I'm in some joint work with Sam Spate, who's here today. We'll be looking at this groupoids, this model of groupoids internal to the category of assemblies. So the exact completion of the category of assemblies is the effective topos, as I said. In some work by Burke and Garner, they show that taking groupoids in terms of a category is a kind of 2-1 exact completion of a 1 category. So in that way, we can think of groupoids internal to the category of assemblies as a kind of 2-1 version of the effective topos. There are various approaches to this. But this is one of them, I guess. Moreover, by the work I've said today, this forms a kind of model of Martin-Löf type theory. And this model of Martin-Löf type theory has groupoids in terms of the category of assemblies as a discrete vibration classifier for modest discrete vibrations. So groupoids in terms of the category of assemblies is a 2 topos in the sense of Mark Webber. And moreover, it is not a Grothendieck 2 topos. So it gives an example of such a thing. But in the type theory side of things, this gives a univalent universe for modest 0 types. So kind of it's a model which has some kind of universe inherent in it. And there's this link between universes and discrete vibration classifiers, which is nice. Moreover, we show that such a thing forms a 2 category with a class of small discrete vibrations, which is a 2-dimensional version of Joyal and Merdijk's categories with class of small maps. So it kind of formalizes the notion of size within the type. So you can think of the modest sets as kind of as the small objects in this category. Great. Some other future work that I'm thinking of doing is doing this for not just internal groupoids, but a kind of infinity version, which is internal simplicial sets or internal cubical objects in some category, which could maybe form interesting new models of homotopy type theory. And also after today, I think there may be some things to say about internal categories modeling directed type theory. I would like to speak to some directed type theory people about that. Okay, thank you very much.